Okay, good. So I was going to say good morning. For me, it is the morning, and for you, it is the afternoon. So thank you for attending my second course. I gave the first one yesterday on the blackboard, but I did not cover as much as I wanted. So I decided that for the second course, I will give it with some slides, which I am going to do now. So let me resume the first course. I started by stating the prime number theorem. And I gave two equivalent formulae for the prime number theorem. One is to look at the sequence of prime numbers, Pn, and the result of the prime number theorem is that Pn is equivalent to n times log n. And the other statement, which is equivalent, is to count the number of primes which are less than a number x, and this is the so-called function, prime number function, which is pi of x, and the result is that pi of x is equivalent to x divided by log x. The number of primes less than x is up to a constant x over log x. And in fact, the quotient of pi of x by x over log x tends to 1 when x tends to infinity. So these are two statements which are equivalent. This is the prime number theorem. I am not going to prove it, but this is one of the main results in the theory. I explained that one important tool in the study of prime numbers is Euler zeta function, which can be defined as the sum for n greater than or equal to 1 of n to the minus s, when s is a real number greater than 1, or a complex number with the real part which is greater than 1. And in this domain, the sum, the infinite sum of n to the minus s, is equal to an infinite product, which is the product for the prime numbers p of 1 minus p to the minus s to the minus 1. So yesterday, I explained that if you take only a finite product, which is the product of the p bounded by some large prime capital P, then you have a limit when capital P tends to infinity, which is the series, which is here. If you take small p less than capital P, the sum that you have is the sum for the integers, which have all the prime numbers, the prime factors, which are less than this capital P. And you take capital P, which tends to infinity. So this is the first result which I proved, but to say that we have the equality between a series and an infinite product requires to define what is a convergent infinite product. And for that, I started by stating what is the logarithm of a complex number, and I gave some explanation on that. And then I gave a precise definition of what are infinite products. And given this definition, where we require that only finitely many factors are 0, and the product for the factors which are not 0 has a limit which is not 0. And so using this definition of infinite product, we have this equality where the right-hand side here is an infinite product now. If you look at S equal 1, the left-hand side is a divergent series. And I explained that this implies that the right-hand side is divergent, is not a convergent product, and therefore the sum of 1 over p, when p is a prime number, is a divergent series. This is the divergence of the harmonic series. The next thing which I did yesterday was to define the Dedekind eta function, which is the same sum, but it is an alternating sum. It is minus 1 to the n to the minus s. And this Dedekind eta function is absolutely convergent for the real part of s greater than 1, but it can be extended with a pole at s equal 1. So the Dedekind eta function can be extended to a function which is convergent for real part of s greater than 0, and this gives an extension of an analytic continuation of the Riemann zeta function for the real part of s greater than 0 with a single pole at s equal 1 with the residue which is 1. And this process, going from the Dedekind eta function to to extend to continue the Dedekind eta function, is a process of accelerating the convergence, which was used by Ramanujan, and which I explained, which gives an analytic continuation of the Riemann zeta function for all the values of S, which are complex numbers, different from 1, because there is a pole at S equal 1. After the talk yesterday, I found that on the blackboard there was a misprint. I said the real part of S greater than K minus 1, and it should have been minus K minus 1, so minus K plus 1. I hope that you corrected yourself this misprint. So this was my course of yesterday. Maybe I could ask whether you have some questions about the course of yesterday. For example, there was an exercise about infinite products, where I say that if you have an infinite product of 1 plus un, if the un are positive, the convergence of the infinite product is the same as the convergence of the series of un. But this is not true if the un are not positive numbers. And I asked to give 2 examples. I hope that you solve this exercise. Otherwise, just tell me. So are there some questions about the course of yesterday? If there are some questions in the chat, I do not see them. I cannot access the chat. Okay, let me. No, I do not see how to access the chat. So if there are some questions, please tell me. Are there questions? No?
I think still no one.
No question. Okay.
Yeah,
so,
no question.
Michel, I have something to ask you. Yesterday, I used the blackboard, and my idea was to use it also today. But I gave a program, and I covered only a very tiny part of the program. And so I thought it's maybe better that today I use slides. So yesterday afternoon, I prepared some slides for this morning. So my question to you is that after my talk, I would like to ask you to tell me what you prefer. So if you could have a survey, and each of the participants would vote whether they prefer when I use the blackboard or when I use the slides. I understand that yesterday it was a blinking, which I am sorry for that. I will try to find another way of putting some light in my office. I am at home here. And so I should take another light which is not blinking. But so forget about that. But apart from that, I would like you to tell me whether you prefer when I use Blackboard. In this case, I go more slowly, but it may be easier to follow. And the slides, I give the link on my website, so it may be more convenient for you. So you will tell me what you prefer, and then I will know when I give some further lectures. Okay, so for this second course, I start with something which is more precise than the fact that zeta of S has a pole at S equal 1 with residue 1. This is just the beginning of the Laurent expansion of zeta of S at S equal 1. It starts with 1 over S minus 1, but the second term is not too difficult to get, and it is gamma Euler constant. I explained yesterday what is Euler constant. It's the limit of the harmonic series, harmonic sum up to n minus log n. So this is gamma. I explained yesterday what is gamma. And so I would like to explain one proof. There are several ways of checking this result. One proof of that this limit is the Euler constant. And for that, I will very briefly give some hints on a very useful tool, which is Abel summation. Abel summation is a bit similar to the acceleration of convergence that I had yesterday, but it is different. We have a sequence of numbers. What are numbers? They are just elements in, say, in a ring. It works for any ring, a commutative ring, say. And so we have a sequence of elements in this ring, A1, A2, up to A capital N. And then we define A capital A sub n as the partial sum of n equal 1 up to small n of AM. And so because of this definition, it's clear that AN can be recovered from the partial sum by taking an minus 1. Yesterday, someone pointed out to me that there was a misprint in what I wrote. I hope this is correct now. And then we take another sequence, Bn, B small n, small b sub n, which is a sequence of elements in the same ring. And we consider the sum of an, bn for n equal 1 up to capital N. And then you can check by hand, it's just a simple computation, that this sum is the sum of capital An, so this one, times Bn minus Bn plus 1, plus kind of reminder, which corresponds to the capital N, which is here, but it is capital An B sub capital N. Okay, and when you check this, you see that you have a telescoping sum, so the terms cancel 2 by 2. This is one formula due to Abel. It's more a method than a formula. And there are several variants of this Abel summation formula. One of them is to replace Bn by the value of a function at the point n. Well, you can say that this is an arithmetic function, but the Abel partial summation formula gives a connection, a link between the sum of an f of n and the integral of capital A of t, f prime of t dt. Capital A of x is the same definition as before, but now we take it for x real number, positive real number. So now an is a sequence of complex numbers. Capital AX is a partial sum up to x, and f is a function of class C1. So it's continuously, you can derivate continuously. And then you look at the sum of an f of n. It's very similar to the previous one, but now the function f is defined on R, and so the sum of an f of n is compared to the integral of a of t f prime of t dt, and there is capital A of x f of x, which corresponds to the upper limit here, which is x. So this is Abel summation formula. Again, you can prove it just by hand. And I will take an example. And the example I take is taking an equal 1, and a of t is the integral part of t. So it's a function which is of class C1 by piecewise. What is capital, the integral part of t? Any real number t can be written as an integer plus the remainder, the fractional part, which is this t with curly brackets, where t is greater than or equal to 0 and less than 1. So this capital T is the largest integer which is less than t. And then you use this formula. So the left-hand side is the sum of f of n. The integral is f of t dt. And the difference between the sum and the integral is the integral from m to n of the fractional part of t, f prime of t dt. And if you use it for the function f of t, which is 1 over t, what you get is, on the left-hand side, the sum of 1 over n, and we take m equals 0. Here, we integrate from 1 to n dt over t, we take log n, and then we have gamma, which comes from this formula, and this gamma is obtained as 1 because we take the sum from 1 to n and not 0. So 1 minus the integral of the fractional part of t dt over t squared. So this gives the difference between the harmonic sum and the logarithm of n. It is a constant gamma, Euler constant, which we find from this formula. This Abel summation formula gives another proof of the fact that the zeta function, Riemann zeta function, can be extended as a meromorphic function for real part of s greater than 0. And for that, you consider an equal n to the minus s. You start with a real part of s greater than 1. You want to approximate this series And an approximation by Abel summation is the integral of t to the minus s dt. But this integral is 1 over s minus 1. We saw yesterday that s minus 1 zeta of s tends to 1 as s tends to 1 by taking positive values of the real part is positive. And if we remove this singularity, the difference becomes an analytic function in C. So this comes also from Abel's summation formula. There is a question? Okay, is there some question? Okay, so the analytic continuation of zeta of s can be obtained as follows. We first integrate from n to infinity t to the minus s minus 1 dt. This integral is easy to compute, and it is 1 over s n to the s. And we use the fact that the sum for n equal 1 up to t of 1 is the integral part of t. And so zeta of s is the sum of 1 over n to the s. So it is s times the sum of the integral which are here. And so you have to make the sum of 1 for n equal 1 up to t. This is the integral part of t. And then when you have this sum which is here, you have t to the minus s, and then the difference, integral part of t minus t dt. And so you get the same result, which is 1 over s minus 1 plus 1. Okay, so we know now that the Riemann zeta function extends to an analytic function. Yesterday, we proved it for all s which are different from 1. Just now, I gave another proof for real part of s greater than 0. And this real part of s greater than 0 will be sufficient. We know that the function zeta of s is defined on the line real part of s equal 1 with s different from 1. For s equal 1, it is a pole. And the result which I would like to prove is that there is no 0 of this function on this real line, real part of s equal 1. I explained yesterday that the zeros of zeta of s play a very important role. They occur in the Riemann hypothesis, and we know that there is no 0 on the real part of s greater than 1, because the infinite product of 1 minus p to the minus s to the minus 1 is convergent and has a limit which is not 0. In fact, we saw yesterday that for the real part of s greater than 1, we can define a function, which is this function on the right-hand side. It is the sum for the prime, the sum for m greater than or equal to 1 of 1 over m p to the ms. So it's a convergent series for real part of s greater than 1. And this is an analytic function in this domain. And the exponential of this function is zeta of s. So we write log of zeta of s equal this function. This is a definition of the function log zeta. We take the real part of the left-hand side. What is the real part of a logarithm? It is the logarithm of the modulus. If you prefer, the modulus of exponential of z is exponential the real part of z. Is that clear? I could switch to share to use my my Blackboard if I can do that. Okay, I don't know whether you see my Blackboard.
Yes, you can see it.
Yeah, you can see?
Yes.
Yeah. So I will just say that. So if you take exponential of z, so it's z is x plus iy. It's exponential x. So x z is in C. Xy are in R. X is the real part and y is the imaginary part. Exponential z is exponential x exponential iy. And the modulus of exponential iy is equal to 1, because y is a real number. And so the modulus of exponential of z is exponential x, which is exponential the real part of z. Or if you prefer, if you write exponential. So if you have u equal exponential of z, so z is the logarithm of u. And if you look at the real part of log u, so this is the real part of z. This is the logarithm of u. This is the logarithm of the modulus of u. It is the same. I hope that this is clear. Okay, let me come back now to so do you still see my screen that I am sharing? It's okay?
Yes, you can see.
Okay, so that's good. It's the first time that I switch from the screen to the blackboard. Okay, so if we take the logarithm of the modulus of zeta of z, we have the real part of what is here. What is the real part of p to the ms? P to the ms, so s is a complex number. It's x plus yt. And the real part of this, so it's a sigma plus it. We have to take the real part, and we have the cosine of mt log p when we take this real part. And now we will use a formula, which is a trigonometric formula. Cosine 2x is 2 cosine square of x minus 1. And therefore, if x is a real number, we get 2 times 1 plus cos x square. You have 2 plus 4 cosine x square plus cosine plus 4 cosine x. But the cosine x square, we replace it by cosine 2x plus 1. And so this is what we find here. 4 cosine x plus cosine 2x plus 3 is always greater than or equal to 0. It's twice a square. Therefore, if you look at this formula for the cosine of mt log p, what you get is the following. You replace, you take this formula for sigma plus it, for sigma plus 2it, and for sigma of sigma, the zeta of sigma. So you first take this formula with the cosine of mt log p. Here you have the cosine of 2 mt log p, and then you have plus 3. So this sum is positive because it's a sum of positive numbers. And this is the logarithm of this modulus. The logarithm of a number, a real number, is greater than or equal to 0. It means that this real number is greater than or equal to 1. So the trigonometric formula proves that if you take a real number sigma greater than 1 and a real number t in R, zeta of sigma plus it to the power 4 times sigma, zeta of sigma plus 2it times zeta of sigma cube. Zeta of sigma is a real number, so I did not put absolute value here. This number is greater than or equal to 1. So this is a low bound for this product. And now we want to prove that there is no 0 of zeta of s on this real line. So we take a sigma which is greater than 1 and which tends to 1. And we look at the 0, the multiplicity of 0 of zeta at 1 plus it and 1 plus 2it. We call this multiplicity of 0 k and L. And so when we have a 0 of multiplicity k, zeta of sigma plus it is equivalent to sigma minus 1 to the k times a constant, which is not 0. Zeta of sigma plus 2it is another constant times sigma of minus 1 to the L, because sigma minus 1 is tending to 0. And zeta, we know that zeta at the point sigma, so sigma tends to 1. So excuse me, this is not sigma plus it. This is sigma. Zeta of sigma is sigma minus 1 to the minus 1. Maybe I can try to correct this. I think it will be better if I correct it. Sorry for this misprint. If you find some misprint, please tell me and I will correct them immediately. Okay, so it was sigma not plus IT, but theta of sigma. Okay, so my screen is no more shared.
We cannot see your screen.
Okay, so sorry, maybe it's not a good idea to correct like this because it takes time. So let me try again to share my screen. Okay, so partager l'écran. Okay, so I will not try again to correct in real time because sorry, I cannot. Okay, so I should be ready soon now. So share the screen. Is it okay now? Can you see the screen?
Yes.
Okay, so I just corrected this misprint here, but I will not correct the misprints now because it takes too much time. So we have this is equivalent to A zeta minus 1 to the K. The next one is B sigma minus 1 to the L. And this one is sigma minus 1 to the minus 1. And so if you look at the power of sigma minus 1 that you have an exponent which is 4K plus L minus 3. And when sigma tends to 1, the left-hand side is always greater than 1. So the exponent has to be negative. And therefore, K it does not tend to 0. So the exponent is negative. And therefore, 4K is less than 3. And so K is equal to 0. So this proves that there is no 0 on the real line, real part of S equal 1. Okay, after this, I will introduce a very important function which plays a fundamental role in the theory, which is Euler gamma function. Euler gamma function can be defined in several ways, but the classical way is the integral gamma of S is the integral of exponential minus t to the s minus 1 dt. So you have an integral, and if you want to say that it defines an analytic function, you have to check that the integral is convergent. When t tends to infinity, there is no problem because you have exponential minus t, which is decreasing very fast, faster than t to the s minus 1. Then t to the s minus 1 is growing. So at infinity, there is no problem. The problem is at t equals 0, and you have to look at what is the convergence of the integral. And for that, you need an assumption, and the assumption is that the real part of S is positive. I will explain that this definition implies that the gamma of S satisfies a functional equation, which is gamma of S plus 1 equal S gamma of S. And thanks to this functional equation, this very simple relation, we can continue analytically this function to a meromorphic function in the complex plane C, with a simple pole at any integer which is less than or equal to 0. There is no pole for the real part positive, but the poles are only at the integers which are less than or equal to 0. If k is a positive integer, there is a pole at s equal minus k, including 0, and the residue is minus 1 to the k divided by k factorial. By the way, 0 factorial is equal to 1. Okay, so to prove that, we integrate by part. By integrating by part, we have exponential minus t to the s, which was here. We had s minus 1. So integrating by part, we find 1 over s exponential minus s to t to the s, this one, which is between infinity and 0. And then we have this. And if you look at this value is 0, and this one is 1 over s gamma of s plus 1. So this gives the formula gamma of s equal 1 over s gamma of s plus 1. But you can replace gamma of s plus 1 by this same formula, and by induction, you find that gamma of s is gamma of s plus n plus 1 divided by s plus 1, s plus n. If you look at the right-hand side of this formula, it is defined, so you have to remove the poles 0, minus 1, minus n, and otherwise, this is defined as soon as the real part of s plus n plus 1 is greater than 0, which means the real part of s greater than minus n minus 1. So you have this equality, which is valid for the real part of s positive. The two members of this equality coincide for the real part of s which is positive. But the right-hand side is a function which is meromorphic for the real part of s greater than minus n minus 1. And therefore, this gives an analytic continuation of the gamma function, because the right-hand side is analytic for this value. So we have now a function which is defined everywhere as a meromorphic function, with the poles which are 0, minus 1, minus 2, minus n, and so on. And there is no other poles. And we can compute by induction the residue at a pole, the pole n plus 1, the pole, okay, we will compute it later, but we can compute the residue and find that it is minus 1 to the n over n factorial. And we deduce also from the formula which was here, that gamma of 1 is 1, and gamma of n plus 1 is n factorial for n greater than or equal to 0. So this is the gamma function. We will be interested in special values of the gamma function, and I start with gamma of 1/2. So gamma of 1/2 is not given by a factorial. It would be for n equal minus 1/2, which does not make sense. But gamma of 1/2 can be computed, not too difficulty, and it is the square root of pi. And the proof is, one proof is the following. We use the definition of gamma of 1/2. We have an integral, and then with the change of variable, we find that it is twice the integral from 0 to infinity of exponential minus x squared dx, just by the change of variable x squared and t. And so if we multiply this formula by itself, we have gamma of 1/2 square. The two, we put it here, we have 1/4. And then we have a double integral, the integral of exponential minus x squared dx times the integral of exponential minus y squared dy. This double integral can be changed, which make a new change of variable by taking polar coordinate. Instead of the coordinates x, y, we take the coordinates r and theta. And with this change of variable, we see that this integral is the integral for theta between 0 and pi over 2, and for r between 0 and infinity of exponential minus r squared, which is this term, and the dx dy becomes r dr d theta. But this can be computed. It is the value of 1/2 of exponential minus r squared between 0 and infinity times pi over 2. and the pi over 2 comes from here. And therefore, you find pi over 4, which gives gamma of 1/2 equal square root of pi. Okay, so this is the special value of the Euler gamma function. The Euler gamma function is defined as the integral from 0 to infinity of exponential minus t to the s minus 1 dt. I told you that the integral from 1 to infinity does not give any problem of convergence. The problem of convergence is the integral from 0 to 1 of exponential minus t to the minus s minus 1 dt. And the idea to expand this is to expand exponential minus t as the series sum of minus t to the n divided by n factorial. This is exponential minus t. And so it's not difficult to check that you can permute the sum and the integral when the real part of s is positive. And then you have a series, which is the integral of this value. But this integral can be computed easily. And this is minus 1 to the n factorial n plus s, which comes from that. You have t to the n plus s minus 1. So it gives n plus s between 0 and 1. And then gamma of s is this series plus an integral which is convergent. So the series which is here defines a meromorphic function of s with simple pole at the negative integers. And as I mentioned before, the residue at minus n is minus 1 to the n divided by n factorial. And the integral on the right-hand side defines an entire function. So this is another way to find the to define the gamma function for all s in C as a meromorphic function. There are other properties of the Euler gamma function which are well known and which I just resume here. I will finally not give proofs, but there is the formula which gives gamma of s, gamma of 1 minus s equal pi over sine of pi s. And I can just say one way to prove that, it is to compare the zeros and poles of both sides. And if you compare the zeros and poles, you see that the two functions have the same zeros and poles, and then you take some limit for s to see that the coefficient which is here will be pi. They could be an exponential, because when two functions have the same zeros and poles, the quotient is an exponential of a function, but there is no exponential here. One way to see that is to look at the growth of the function. There is this other formula, gamma of s over 2, gamma of s plus 1 over 2, which is gamma of s times 2 to the 1 minus s and some constant. There is a limit for gamma of s, which is n to the s n factorial divided by s plus 1 s plus n. And there is an infinite product, which is the infinite product which is here. It's not too difficult to see that the two formulae here are equivalent. For the last formula, this is something which we essentially saw yesterday when I explained the process of Weierstrass to construct a function with given zeros. 1 over gamma of s is an entire function with zeros at the point s equal minus s minus n and s equals 0. So 1 over gamma of s can be written as s times this infinite product, and we multiply by exponential minus s over n in such a way that this infinite product is convergent. The expansion of the logarithm of 1 plus s over n starts with minus s over n, and the next term is s squared over n squared, and the sum of 1 over n squared is a convergent series. And then we have a function which will be an exponential function. It turns out that this exponential function is exponential gamma s, and gamma here is again Euler constant. And for that, again, you can look at the growth of these two members and see that this function should be of the form exponential a plus bs, and we compute a and b by taking some special values. Okay, so there is another way to prove the analytic continuation of zeta of S. And this other way is to prove the following formula. Zeta of S is 1 over gamma of S times the integral from 0 to infinity of 1 over exponential of t minus 1, t to the s dt over t. So this gives a connection between zeta of S and gamma of S. This formula will be very useful for studying the zeta function. And this formula, one proof is the following. You look at this integral, which is here. You have 1 over exponential of t minus 1. You expand this using always the same formula. It's the sum of exponential minus nt for n greater than or equal to 1. And so you replace this quotient here by this series, and you have to integrate exponential minus nt t to the s dt over t. And what you find is just gamma of s divided by n to the s, because you make a change of variable. You take nt equal u, and then you find gamma of s, which is given with the s, which is here, t to the s minus 1, if you prefer here. And so this gives the proof of this formula. And now you can check that the right-hand side is an analytic function, and this is something which is very general. This is the analytic continuation of function, which is an integral of from 0 to infinity of f of t, t to the s dt over t. So in this example which we have here, the function f of t is exponential minus nt. If you take f of t equal exponential minus nt, you recover the formula which was earlier. And so the lemma, which I will not prove, but which is a classical lemma from complex analysis, is that if you take a function which is C infinity defined over the positive real numbers, you assume that it is a fast decreasing function, like exponential minus nt. So at infinity. And you define a function as by an integral, which is 1 over gamma of s, the integral of f of t, t to the s dt over t. This function has an analytic continuation to C, and we have some formula for the special values of this function where s is equal to minus n, and the value of this function at s is equal to minus n is minus 1 to the n times the derivative of f of order n at 0. And so this will be quite useful for the zeta function, that because we have to look at the derivative of some function which is t over exponential of t minus 1. And so we will use this formula for the function f of t, which is t divided by exponential of t minus 1, which is the sum of the exponential minus nt. So we look at this function, t over exponential of t minus 1. We check that the hypotheses of the lemma are satisfied. And so if we want to compute the special values of zeta, we have to look at the expansion, Taylor expansion of this function at 0. So we define the Taylor expansion at 0 as the sum of bn t to the n over n factorial, and bn are just the coefficients of the Taylor expansion. So this defines the sequence bn, which is the sequence of Bernoulli numbers. So the first values are b0 equal 1, b1 minus 1/2, b2 equal 1 over 6, b4 is minus 1 over 30. You have to be careful that in the literature, sometimes there is a change of index compared to what I say here. Sometimes this is defined as b1 equal 1 over 6, b3 equal, b2 is 1 over 30, because the odd values are 0. This comes from the fact that if you take f0 of t minus 1, then this is an even function. So the coefficients of odd index are 0, apart from the first one, which is b0, which is 1. So it starts with t, and then even function. So this is the sequence of Bernoulli numbers, which again will play a very important role. And I have here a table of the values of the Bernoulli numbers for the first even values of n, 2, 4, 6, and so on. And I write below bn over n because these are the numbers which will occur as the values of the zeta function at the negative integers. I do not insist on this page. So we have seen that zeta of s was an integral. It is this integral which is here. The poles of this function, we have the poles of the zeros of gamma of s. Well, we have the poles of gamma of s, and then we have the poles of the function which is here. For gamma of s, the poles are 0, -1, -2, and we have seen that the residue is -1 to the n over n factorial for s equal -n. For this integral, we check that the poles are 1, 0, -1, -2, which correspond to the values of the s which is here, if s is equal to -1, 0, and 1, 0, -1. And the residue is bn plus 1 over n plus 1 factorial at s equal -n. So we check that the poles cancel except for s equal 1, and this is why the zeta function is meromorphic in C with a single pole at s equal 1. All the other poles just cancel. And from what I explained, we deduce the values of the Riemann zeta function at the negative integers. For n, a positive integer, zeta of -n is -1 to the n, bn plus 1 over n plus 1. In particular, zeta of -n is a rational number when n is positive, so -n is a negative number, and zeta of -2n is 0 for n greater than or equal to 1. So I mentioned yesterday the trivial zeros of the Riemann zeta function and the non-trivial zeros. The trivial zeros are the s, such that zeta of s is 0 and s as a real part which is not between 0 and 1. And the trivial zeros are the -2n for n greater than or equal to 1. So this is the so-called trivial zeros. And so we know that apart from the -2, -4, and so on, the zeta function has no zero outside what I defined yesterday as the critical strip. So these are the trivial zero of zeta. And the other numbers are non-zero. So we have zeta of 0, which is -1/2, which comes from the first coefficient b1. When you take n equals 0, you have b1 here and -1 to the 0. And then you have zeta of -1, which is -1 over 12, zeta of -3, which is -1 over 20. And you see that this gives the values of the Riemann zeta function at the negative integers. After we have seen the negative integers, which are not so obvious, because the value zeta of 0, zeta of -1, zeta of -3 are not given by the infinite series. In fact, Riemann explained the extension as a meromorphic function, but Euler found the values of zeta of 0, zeta of -1, zeta of -3, but he wrote the sum of 1 over n to the s, and he gave the values -1/2, -1 over 12, by using what is called divergent series. And the values that Euler found using divergent series are the right one. These are the one that Riemann proved to be the values of the extension of the Riemann zeta function at the negative integers. Okay, so after the negative integers, we look at something which is maybe easier to understand, which is the values at the positive even integers. We will say a few words about the positive odd integers, but let me say right now that very few things are known on the positive odd integers. So we consider the positive even integers. And Euler proved that zeta of 2n divided by pi to the 2n is always a rational number when n is an integer which is strictly positive, at least 1. For example, zeta of 2 is pi square over 6, zeta of 4 is pi 4 over 90, and so on. I will give some explanation on this result of Euler, and especially on the first value, which is zeta of 2, which is pi square over 6. And I would like to expand a little bit this result. It was called the Basel problem, and it was asked by Pietro Mengoli in 1644. Pietro Mengoli asked what is the exact value of the sum, which we call zeta of 2, which is 1 plus 1, 4 plus 1 over 9, and so on. And the answer is 1.644934. But he asked a closed formula, as we say. So this is Pietro Mengoli, and it is called the Basel problem because Pietro Mengoli was in Basel. The Bernoulli family was originally from Antwerp, but at that time in the Spanish Netherlands, Antwerp was in the Spanish Netherlands, but the Bernoulli family emigrated to escape the Spanish persecution of the Huguenots. And after a brief period in Frankfurt, the family moved to Basel in Switzerland. And this is where they studied number theory. And the Bernoulli family is just very extraordinary because there were many mathematicians in this family. The oldest one was James or Jacques Bernoulli or Jacob Bernoulli, was a mathematician, and the Bernoulli numbers were were found by Jacob. And Johann Bernoulli, who was named also Jean, was an adopter of the infinitesimal calculus. So these are the oldest members. There is Nicolaus II Bernoulli, who worked on curves, differential equation, probability. Daniel Bernoulli, who developed the Bernoulli paradox and St. Petersburg paradox. Johann II Bernoulli, a mathematician and physicist. Johann III, astronomer, geographer, and mathematician. And Jacob II, physicist and mathematician. So when you speak of Bernoulli, you have to be more precise if you want to say exactly which member of the family you mentioned. So when the Bernoulli tried to find these values, there were similar series which were known. In particular, if you take the series 1 over 1, 2, plus 1 over 2, 3, plus 1 over 3, 4, you can replace 1, 2 by 1 over 1, 2 by 1 minus 1 half. 1 over 2, 3, you can replace by 1 half minus 1 over 3, and so on. And we have seen that this gives log 2. In fact, there are some other series which are very similar to that, which gives a number which is an integer, like the sum of 1 over n plus 1. So to know when you have such a series, whether you will find a rational number, a transcendental number, is something which is not quite obvious. It really depends on the series. So such expansions were known by Leibniz and by Johann Bernoulli. And there were some other similar series. So for the first one, it just comes from the expansion of log 1 plus t that we have seen also. So this was the first example that I mentioned. For the Basel problem, sum of 1 over n squared, then Daniel Bernoulli found an approximate value, which was 1.6. Goldbach found a value which was 1.6445, and Euler computed it in 1731, and he found some more correct decimals. So there was a lot of activities around this problem. And it is in 1735 that Euler found finally the exact value, and the exact value is pi square over 6. And Euler became famous at that time because it was a famous open problem, and he was only 28 years old. The sketch of proof of Euler is the following. If you take a polynomial f with f of 0 is equal to 1, you write 1 plus a1z plus a2z squared plus anz to the n. But you look at the complex roots, and if the complex roots are alpha 1, alpha n, this polynomial factors as 1 minus alpha 1z times 1 minus alpha nz. And you look at the coefficient a1. The coefficient a1 is just minus the sum of the root. It's the coefficient of z, so it's a minus alpha 1, minus alpha 2, minus alpha n. So alpha 1 plus alpha n is minus a1. And so if you consider the function sine s over x, you can write it 1 minus x squared over 6 plus x4 over 5 factorial, plus and so on. And if you replace x by the square root of z, you have the sign of square root of z over z, which is a good series, which is here. And if you look at the zeros of this function, you have pi square, 4 pi square, 9 pi square. And so Euler said, what is true for the polynomial should be true for this function. The sum of the zeros is the sum of the inverse of the zeros is the sum of 1 over n squared pi square, and it is minus 1 over 6. And the sum of the inverse of these numbers should be sum of 1 over n squared pi square equal 1 over 6. This is the sketch of proof of Euler. Now there is a small problem with this proof. We want to extend the result from polynomial to series. And if you take a series 1 plus a1z plus a2z squared plus and so on, if you multiply by a function which has no zeros, then exponential of lambda z, the product exponential lambda z times f of z start with 1 plus a1 plus lambda z plus and so on. So the sum of the inverse of the zeros cannot be at the same time ai and 1 plus ai, 1 over ai plus lambda. So the sum of the alpha I cannot be at the same time minus ai and minus ai minus lambda. So there is something which is not working, because you could replace this function by the product of this function with a function of z which does not vanish, and you would get another coefficient for z. So how to fix this problem? Because the proof is not complete, but the result is correct. To fix this problem, one way is to write sine x over x, which occurred before, as an infinite product, and to prove that when you have this infinite product, the two members have the same zeros, but there is no exponential here. So it's really sine x over x is the product of 1 minus x squared over n squared pi squared. And therefore, the first term in the expansion, the coefficient of x squared, is the sum of 1 over n squared pi squared, and it is 1 over 6, because this is the expansion of sine x over x. And so this gives a complete proof of the formula, provided that we take for granted this formula which is here. And I will explain one proof of this product expansion of sine x over x. You see that it's a product expansion which is similar to what I explained yesterday for the Riemann, for the Weierstrass product expansion. So I give one proof for evaluating zeta of 2. There is a paper by Robin Chapman, who is giving 14 proofs of the zeta of 2 equal pi squared over 6. So don't believe that there is a single proof. There are many proofs of that. Okay, so I would like to explain one proof of this expansion of sine x over x. For that, we start with the cotangent function, which is cosine x divided by sine x. And I will first prove an expansion of the cotangent of x when x is a complex number which is not a multiple of pi, so that sine x is not 0. And the expansion which is valid is the following. The cotangent of x is 1 over x plus 2x times the sum from n equal 1 up to infinity of 1 over x squared minus n squared pi squared, which correspond to the fact that the numbers x equal plus or minus n pi, which means the multiples of pi z, of pi, are poles of the cosine, of the cotangent. They are zeros of the sign. And so the proof of this proposition, one proof, is the following. We consider the function cotangent of z, which is cosine of z divided by sine of z. It is meromorphic in C. It is odd. If you replace z by minus z, you change the sign. It is periodic of period 2 pi, like the cosine and the sine. And the poles are the zeros of the sign. They are simple, and they are the multiples of pi with n in z. We consider the function z gives cosine of z divided by z minus x sine of z. We consider this function, and we consider the integral for a large disk, modulo of z equal r, of cosine of z divided by z minus x sine z. We take this integral, and we use the residue formula of Cauchy, and for that, we write this integral as the sum of the residue. There is the 2 pi I, which is here. The r that we choose will be 2n plus 1 pi over 2, with n an integer. And using this radius and n tending to infinity, one checks that the left-hand side tends to 0 when capital N tends to infinity. This is not completely obvious because you have the integral for modulo of z equal r, which gives 2 pi r, the 2 pi cancel, but the r is what is important. And you have the z here, which has modulus r. And so it seems that you have r divided by r, which is does not tend to 0, but you have to use the fact that the function is odd. So there is a small work to be done to check that this integral tends to 0. And now we need to know what are the residues of this function. The poles are at z equal x, because z minus x, at z equal 0, n positive and n negative. At z equal x, we have the cotangent, cosine x divided by sine x. At z equal 0, we have 1 over x, minus 1 over x for the residue. And we have the residue at z equal n and z equal minus n, which gives minus 1 over x minus n pi. But if n is negative, minus n is the same as plus absolute value of n. So this will give minus 1 over x minus n pi, minus 1 over x plus n pi for the n which are greater than 1. We put 0 apart, and the n are inside the disk on which we are integrated. We integrate on the circle. And so we have n which is less than r, x squared minus n squared pi squared, which correspond to the sum of these two ones. So when we have that, we take a capital N which tends to infinity, and we get the formula which is here. Cotangent is 1 over x plus 2x. We will use again this formula a little bit later. Now, I wanted to prove that the sine z is z times the product of 1 minus z squared over n squared pi squared. And so we consider this function, h of z. We want to prove that it is the sine of z. For that, we have an infinite product. It is natural when we have an infinite product to take the logarithmic derivative. And the logarithmic derivative is h of z, h prime of z divided by h of z. We take the logarithmic derivative of z, which is 1 over z, the logarithmic derivative of that, which gives 2z over z squared minus n squared pi squared, and we recover the cotangent of z because of what we proved just before. If we take the logarithmic derivative of h of z divided by sine of z, for h, the logarithmic derivative is h prime over h. For the sine, the logarithmic derivative is the cotangent, and therefore, the logarithmic derivative of this function is 0 everywhere apart from pi z, but by analytic continuation, it means that the logarithmic derivative is 0 everywhere, and therefore the function is a constant. And then you look at what happens when z tends to 1. For sine z over z, the limit is 1, and for h of z over z, also the limit is 1. So h of z is sine of z. So this completes the correct proof of Euler for zeta of 2 equal pi square over 6. There is another proof which is nice, which is in the same spirit as other parts of my courses. The one reference is a lecture by Pierre Cartier in the Bourbaki seminar, and the proof is attributed to Calabi. And the proof is the following. You expand 1 over 1 minus x squared y squared as the geometric series. We use this formula very often. We integrate from 0 to 1 for x to n, and from 0 to 1 for y to n. And so if we have this double integral of the left-hand side, we have a sum of 1 over 2n plus 1 square. So we get the sum of the inverse of the squares of the odd numbers, only the odd numbers here. Now we want to compute this integral here. And for that, we make a change of variable. We replace x, y by u and v, where x is sine u over cosine v, and y is sine v over cosine u. And so when we make this change of variable, we have an integral for u and v, and there is the domain, which is u less than pi over 2 and positive, v is also less than pi over 2 and positive, and u plus v is less than pi over 2, which corresponds to the domain of xy. And this integral is easy to compute. It's just the area of this domain, and the area is pi square over 8, which corresponds to the pi which are here. So we get the sum of the 1 over 2n plus 1 square as pi square over 8. It's not exactly the formula, but after that, it's easy to recover the formula for zeta of 2. We have this sum, which is pi square over 8. We are interested in the sum of 1 over n square, and we split it into two parts. We take the even values and the odd values. For the odd values, we know this here. For the even values, in fact, we have 1/4 of zeta of 2. And so zeta of 2, which is the sum of 1 over n square, is 4 over 3 times the sum of the odd values, and 4 over 3 times 1 over 8 gives 1 over 6. Okay, so this is another proof. I would like to say something again about zeta of 2, which is that zeta of 2 is a period. What is a period? I will not say too much about periods, but it's just that the zeta of 2 can be written as an integral of a domain which is defined by inequalities involving just rational numbers. So we integrate some function, which is a rational function, 1 over t1 times 1 over 1 minus t2. It's a rational function with rational coefficients. And zeta of 2 can be written as this integral. And the proof is the following. What is this domain? We integrate for t1 between 0 and 1, and for t2 between 0 and t1. So t1 goes between 0 and 1, and t2 goes from 0 to t1. We will integrate dt1 over t1, and here for t2, we integrate dt2 over 1 minus t2. We expand 1 over 1 minus t2, as usual. We have this series, and now we check that we can integrate, permute this sum and this integral. And so we have the sum for n greater than or equal to 0 of the integral of t2 to the n dt2, which is the same as t1, which was the upper limit here, t1 to the n plus 1 over n plus 1. Okay, so this is the computation for the integral for t2. And now, again, we check that we can permute the sum and this integral. So we have the sum of 1 over t(n plus 1 times the integral between 0 and 1. And what we have here is t1 to the n, because there is one t1 which cancels. And again, this gives 1 over n plus 1. And so we have the sum of 1 over n plus 1 square for n greater than or equal to 0. So this is zeta of 2. What I did for zeta of 2 can be done for any non-negative integer, for any integer which is at least 2. And the formula is the following by induction. Zeta of s is the integral for 1 greater than t1, greater than t2, greater than ts, greater than 0. Then we have dt1 over t1, dts minus 1 over ts minus 1, and then dts over 1 minus ts. The proof by induction is easy, but it helps if you prove by induction the formula which is here. So you do not go to T1, you go only up to T1, not to 1, but to T1 only. And so you forget about dt1 over T1, you compute this, and you find that it is a sum of T1 to the n minus 1, n to the n minus 1, s minus 1. So this is easy to prove in this way, by induction. Okay, so I am interested in the values of the Riemann zeta function at the positive integers. And for that, I will again use the expansion of pi times cosine of pi z that we have seen before. There was no pi in the formula before, but we just make a change of variable. We replace z by pi z. And what we find is that pi cotangent of pi z is 1 over z plus the sum of 1 over z plus m plus 1 over z minus m, which gives the 2z divided by z square minus m square for m equal 1 up to infinity. So this is the formula which I proved before. And now we expand the the sum which is on the right-hand side. We have 2z over z square minus m square. We want to use again the geometric series. So we want to expand 1 over 1 minus z square over m square. So we have a coefficient here, which is 2z over m square. And when we expand that, we have the sum of z to the 2k plus 1, m to the 2k plus 2. And now we have to make the sum for m equal 1 up to infinity of this series. And so we have the sum of over m of 1 over m to the 2k plus 1. K was starting to 0, we change k plus 1 in m, and so n goes from 0 to infinity. We have zeta of 2n and z to the 2n minus 1. So we have an expansion of pi cotangent pi z as around 0 as a meromorphic function. So it is a Laurent expansion. There is a residue at 0, which is 1. So we have 1 over z plus a series which is with the coefficient, which are the zeta of 2n. So this is the Laurent expansion of pi cotangent pi z. But there is another Laurent expansion which is easier to obtain, which is by using the definition of the cotangent as the quotient of the cosine by the sine, and you expand this by writing that you have I pi plus 2I pi divided by exponential 2I pi z minus 1. So just by writing exponential 2I pi z minus 1 plus 2. So you have the 2I pi. And so this 1 over exponential 2I pi z minus 1 is something that we have seen before. This is given by the Bernoulli numbers. So pi cotangent of pi z starts with I pi plus 1 over z times the sum of bn, 2I pi z to the n over n factorial. If you take z equal 1, you see that the I pi which is here will cancel. So this is why you have I pi which is imaginary, but it's coherent. So you have two expansions of pi cotangent pi z into a Laurent expansion. You have one which is given by the formula which is here, starting with 1 over z, and you have one which is given by the Bernoulli numbers. And so you deduce the value of zeta of 2n in terms of bn. And the result is the following. If n is a positive integer, zeta of 2n is minus 1/2 of b2n, 2I pi to the 2n, divided by 2n factorial. Zeta of 2n is a positive number. because n is greater than 1 and it is a sum of positive numbers. You have a minus I here, but you have a I to the 2n. So I to the 2 is minus 1. And so the sign, just taking into account the sign of b to n, you deduce this formula where the right-hand side is a positive number. It's a positive, it's a rational, positive rational number times pi to the 2n, which is something which I announced before. And from that, you deduce the first values of zeta of 2, zeta of 4, zeta of 6, and so on. So this was done by Euler, but it was after he solved the Basel problem. He was able to compute all the even zeta values. We have seen the values of zeta at the positive integers and the positive even integers and at all the negative integers. And so we can ask whether there is a connection between these values because they have some similarity between zeta of 2n and zeta of minus m. And the answer is yes, there is something strong, which is the functional equation of the Riemann zeta function. I have introduced the gamma function, the zeta function, and if you multiply gamma of s of 2 over 2 by zeta of s with this coefficient, you get a function xi, which is an entire function. There is no pole because we have multiplied by ss minus 1 to remove all the poles. It is analytic in C, and this function has the values at 0 and 1, which is 1, and satisfy the functional equation zeta xi of s is xi of 1 minus s. So this is very, very powerful because you have a connection between the the positive values with the real part of s which are greater than 0 and the values where 1 minus s which correspond to the real part which is negative. And so we have some symmetry, which is this given by this functional equation, which relates s and 1 minus s. So it relates the two connected components of the complement of the critical strip, but it also relates the two halves of the critical strip, which are the real part which is between 0 and 1/2, and the real part which is between 1/2 and 1. So we just have to look at the Riemann zeta function for the real part greater than or equal to 1/2, and then if we know the Riemann zeta function on this part, we know it on the other part. So I come back to the non-trivial zeros. We consider the set of zeros of the Riemann zeta function in the critical strip. I say here the multiset, which means that we count multiplicities. We repeat the zeros if they occur with multiplicities. By the way, we do not know a single example where a zero of the Riemann zeta function will have multiplicity greater than 1. The conjecture is that all the zeros of the Riemann zeta function are simple zeros, but we do not know it. So we include the multiplicities just in case some of the zeros would not be simple. And then we look at the zeros of zeta of s, which have a positive imaginary part. And then if we know the one with a positive imaginary part, then we know all the zeros because of this formula. Z plus is Z union 1 minus rho, where rho is in Z. So this gives a connection between the zeros in the which have a positive imaginary part and the one with a positive negative part. So Z is the set of all zeros. There is a product expansion which is due to Hadamard for xi of s, which is the function which is here. And the zeros of xi of s are exactly the zeros of zeta, which are the non-trivial zero, which means that there are the elements of Z in the critical strip. And this is something which is not too surprising according to what I said yesterday on infinite product. You have the product of 1 minus S over rho. You do not have S because there is no zero at S equals 0, but you want this to be convergent, and for that you have to multiply by an exponential of S over rho. And then you have some function which has no zero. It turned out that this function is minus exponential bs, where some b, which is an explicit constant, minus gamma over 2, minus 1 plus 1/2 log of 4 pi. So it's quite a nice constant. Of course, we do not know whether this constant is rational or not, but we know the expansion of this constant. We can group the zeros with the one of positive imaginary part and the one of negative imaginary part. And in this case, this product becomes the product only for the one with positive imaginary part of 1 minus S over rho, 1 minus S over 1 minus rho. Thanks to that, we can take the logarithmic derivative of zeta, and using the logarithmic derivative of xi, we find zeta prime over zeta, which is 1/2 log pi plus 1/2 gamma prime of S over 2 over gamma of S over 2, the logarithmic derivative of gamma. We have minus 1 over S minus 1 over S minus 1, which comes from the factor SS minus 1, and then the sum of 1 over S minus rho. This is an explicit formula for the logarithmic derivative of the Riemann zeta function. I will just say a few words about the next development of the subject, and especially to explain where this formula comes from, the formula which relates xi of S and xi of 1 minus S. It comes from a Poisson formula. If you have a function which is integrable on R, and its Fourier transform, which is f hat of y, which is the integral of f of x exponential 2i pi xy dx, if the function x gives the sum of x plus n is continuous with bounded variation, then you have the sum of f of n, which is the same as the sum of f hat of m. Well, if you saw it in the course, then it's okay. If you never saw it, I will not say too much about it, but I will just say that using this formula, if you look at the theta series, theta of u, which is the sum of exponential minus pi u n square for n in z, then it satisfies the functional equation. The theta of 1 of u is square root of u theta of u. And thanks to that, we prove that xi of s is ss minus 1 times the integral of theta of u minus 1 u to the s over 2 divided by 2u du. So this is an integral formula for the xi function. I would like to look at the Riemann memoir, which is just 9 pages, which is in German, and it is translated in many languages, including in English. And the title in English is On the Number of Primes Less Than a Given Magnitude. So this is what we call pi of x, the number of primes less than x. So in this memoir, Riemann considered the function zeta of s, which is defined by the series. He proved that there is an analytic continuation to the whole complex plane, even if it does not use the word analytic continuation. And in the complex plane, this function is holomorphic, except a simple pole at s equal 1 with residue 1. So we have seen that, but this comes from the Riemann memoir. He proves a functional equation, which is xi of s equal xi of 1 minus s, and which is written in this way, which is here. It is the same. He proved that this function, which of course it does not call the Riemann zeta function, he proved that it has simple zeros at -2, -4, -x. These are the trivial zeros. And he proved that there are infinitely many non-trivial zeros in the critical strip, which means that there are number rho equal beta plus I gamma. Beta is between 0 and 1. This is the critical strip, and gamma is in R. So he proved that there are infinitely many non-trivial zeros, and I will explain one proof of this fact. he proved the product formula, which I just mentioned, which is a product for rho of 1 minus S over rho. And he gives also an expansion of the sum of lambda of n. This is the von Mangold function which I defined yesterday. And this is related with the logarithmic derivative of the zeta function of Riemann. And then in this paper, he states the Riemann hypothesis, which is that every non-trivial zero of zeta of S is on the critical line, 1/2 plus I gamma. But he said that he does not claim to have a proof. He just says that this is a result that he believes to be proof, but he did not spend too much time to try to prove it, he says. So the Riemann hypothesis is that the complex zeros of the Riemann zeta function in the critical strip lie on the critical line real part of S equal 1/2. If zeta of S is 0 and the real part of S is between 0 and 1, then the Riemann hypothesis is that the real part of S is 1/2. There are many equivalent statements. One of them, which is probably the most well-known equivalent statement, is to give an estimate for pi of x in terms of the function Li of x, which is the so-called logarithmic integral. It is the integral from 2 to x of dt over log t. You see, the prime number theorem says that pi of x, the number of integers less than x, which gives the title to the memoir of Riemann, is equivalent to x over log x. But this is much more precise because the Li function, which is given by this integral, has an expansion which is x over log x plus x over log x squared plus and so on. And it would mean that pi of x is this function with an error term which is much slower than all the expansion which is given here. So this would be a very precise statement for the number of prime numbers less than x. It should be Li of x. But this is not known. There are some notes by Riemann on non-trivial zeros, and he computed the first non-trivial zeros. And if you look at the internet, you will find many zeros which have been computed with many decimals. And these references are on the online encyclopedia of integer sequences, which has a lot of information on many sequences. And this table is from the online encyclopedia of integer sequences for the reference, which is Riemann zeta function. We are interested in the non-trivial zeros of zeta of S. The first to prove that there are infinitely many non-trivial zeros on the critical line is Hardy in 1914. Riemann proved that there are infinitely many non-trivial zeros, which means in the critical strip, but Hardy proved that infinitely many of them are on the critical line. And now we know that a positive percentage of these zeros are on the critical line. Levinson proved in 1974 that at least 1/3 of the non-trivial zeros are on the critical line. And in 2020, it was proved that at least 41%, 41.60% of the non-trivial zeros are on the critical line. So it's not yet, we are not yet at half of the zeros. But even if we prove that 100% of the zeros are on the critical line, it could be that there are infinitely many which are not on the critical line. So this is the state of the art. Okay, just a sketch of proof that there are infinitely many non-trivial zeros, so which means in the critical strip. We consider the function xi of S, which we introduced before, and we look at the growth of this function. What is the growth of a function? A function has order rho if it grows like the exponential of r to the rho. Maybe, no, I don't have much time to write it on the board. But we say that the order is 1 if it grows like exponential capital R to the 1 plus epsilon. So f of z is exponential r to the 1 plus epsilon. If we take the logarithm, we get r to the 1 plus epsilon. If we take one more the logarithm, we have 1 plus epsilon log r. We divide by log r, and we have 1 plus epsilon. So for all epsilon, f of z is bounded by exponential r to the 1 plus epsilon for r sufficiently large. I will tell you why we need this estimate. The zeros of psi are the non-trivial zeros of zeta, as we have seen looking at this right-hand side. And it satisfies the functional equation psi of z, z is psi of 1 minus z. If you consider the function f of z, which is f of 1/2 plus z, so we just shift by 1/2, this functional equation becomes f of minus z equal f of z, which means that f is an even function. It's a sum of even powers of z. So if you replace z by square root of z, you find an entire function of order 1/2. So it grows like exponential r to the 1/2, such that f of z is g of z squared. Now, g is not a polynomial, and there is a factorization theorem of Hadamard, which gives this product of 1 minus z over zi, and there is no exponential here, because the order would not be 1/2. So this is just this product. But g of z, it's easy to see, psi of z is not a constant, and so g is not a polynomial. G of z is not a polynomial, and so this product is infinite. And this proves that g has infinitely many zeros, and therefore psi also in the critical strip. We know much more about the number of zeros in the rectangle, which is here inside the critical strip. We know that it varies like t log t, essentially. It's t over 2 pi times log t over 2 pi e, plus a big O of log t. So it's rather precise, because we have t log t plus something which is very small. So we know how many zeros there are. And to prove the prime number theorem, Hadamard and Delahaye-Poussin had to find a domain, a zero-free region for zeta of s. We have seen that zeta of s does not vanish for real part of s equal to 1. In fact, there are some proofs of the prime number theorem which do not need a zero-free region. But Delahaye-Poussin proved that the zeta function does not vanish if sigma is greater than 1 minus a small function which tends to 0 when t tends to infinity. So you have the critical, you have the line sigma equal 1, and you go a little bit on the left, so inside the critical strip. And there are some better results which are known on this result by Korobov and Vinogradov for some zero-free region. Okay, I still have 10 minutes, I think. Is that right? Yes, I have 9 minutes. I would like to say a few words on my own interest in number theory, which is transcendence, irrationality, transcendence, algebraic independence. And I say something about the even values of the Riemann zeta function at the positive integers, zeta of 2, zeta of 4, and so on. And we have seen that the zeta of 2n is a rational multiple of pi to the 2n. What about zeta of 3, zeta of 5, zeta of 2n plus 1? We know almost nothing concerning the arithmetic nature of these numbers. What is expected is that there is no formula similar to the fact that zeta of 2n divided by pi to the 2n is a rational number. The conjecture, and there are several reasons to make this conjecture, is that if you take any polynomial with rational coefficients in pi, zeta of 3, zeta of 5, zeta of 2n plus 1, then if the polynomial is not 0, then the polynomial will not vanish at this point. For example, if you take zeta of 3 minus p over q, it should never be 0. And if you take zeta of 2n plus 1, it should be an irrational number, and even it should be a transcendental number. So this is the conjecture. But we are very far from proving it. It was proved only in 1978 that zeta of 3 is an irrational number. We conjecture that it is transcendental, but we only know that it is irrational. We do not know whether zeta of 5 is irrational or not. What was proved by Rivoal in 2000 is that if you look at all these numbers, infinitely many of them are irrational. And even more, the vector space, Q vector space spanned by these numbers has a dimension which is infinite. But this does not give the irrationality of any of them. Zudili in 2004 proved that if you take the four numbers, zeta of 5, zeta of 7, zeta of 9, zeta of 11, one at least is irrational. We conjecture that all of them are irrational and even transcendental, but we only know that one of them is irrational. So this is what we call the non-effective result. We cannot produce an irrational number, but we know that there is one. Why do we are confident that this result is true? The result is the following. We want to prove that these numbers are algebraically independent. So we have some zeta of S, zeta of S1, zeta of S2, and we are interested in polynomial in zeta of S1, zeta of S2. So we are interested in taking product, zeta of S1, zeta of S2. And when we take product, what we find is some generalization of Euler values to several variables, S1, Sk. And so if you take S1, Sk positive integers, where the Si are at least 2, Euler defined zeta of S1, S2, Sk as the sum, and now it's a sum for n1 greater than n2 greater than nk of 1 over n1, S1, nk, Sk. So these are the multiple zeta values introduced by Euler again, and he studied them. These numbers are periods. I mentioned what are periods before. And so in terms of integral, they are very similar to the zeta of S that I defined before. Only now, if you have 2, 1, zeta of 2, 1, you have 1 minus T2, 1 minus T3. And the proof is very similar to the proof which I defined before. We have the sum of 1 over m squared n, which is zeta of 2, 1, when you integrate that. So a consequence of this formulae is that the multiple zeta values satisfy a lot of independent linear relations with integer coefficients. We can multiply the series, and if you multiply sum of 1 over n squared by sum of 1 over k squared, you will find zeta of 4 plus 2 times zeta of 2, 2. But you can also use the integrals and multiply the integrals. You find another integral, and you find zeta of 2 squared equal to zeta of 2, 2 plus 4 zeta of 3, 1. And using that, you find some interesting relation. Zeta of 4 is 4 times zeta of 3, 1. You use the product of series and the product of integrals. And the fact is the following. The zeta values, the multiple zeta values, are sufficient to obtain the linear relations among all the zeta values. So let me, maybe I will try to shift to the blackboard. And okay, so okay, do you see my blackboard? Do you see it?
Yes. Yes.
That because it's something which is rather simple. When you have zeta of S, we are interested in polynomial in zeta of S. So we have to take zeta of S1, zeta of S2, and so on. And zeta of S1, zeta of S2 is a linear combination of MZV. The MZV are the values like zeta of T1, T2. In fact, it's sufficient to take two variables, and zeta of T1, T2 are the ones that I defined just before. And in general, any monomial in zeta of S, where S are greater than or equal to 2 integers, are linear combinations so S is just an integer here, are linear combination of multiple zeta values, which are zeta of T1 En. So using these multiple zeta values, we replace the problem of algebraic independence, which is the linear independence of monomials. A polynomial is a linear combination of monomials, by a problem of linear independence. If we know all the linear independence relation between the MZV, then we know all the algebraic relations between the zeta function. So if we know all linear relations among MZV, then we know all algebraic relations among zeta values. So we have shift from a problem of algebraic independence, which is difficult, to a problem of linear independence, which a priori is easier. And we have some good conjecture about the dimension of the space spanned by multiple zeta values. And there's some work of well, many people, Zagier, Brown, and other people, which give the conjecture dimension of the space, linear space. Okay, so I think I will just add one slide. I mentioned the gamma function, and there are some open problems related with the gamma function, which are again related with transcendence and algebraic independence. And the conjecture of Röhrlich-Lang is that if you take the values of the gamma function, all the algebraic relation among the values of the gamma function are should be deduced from the properties of the gamma function itself. Maybe I will just end, because I think it's time now. I will just say what is known. What is known for the gamma function is that gamma of 1/2, gamma of 1/3, gamma of 1/4 are transcendental. But for gamma of 1/5, we do not know whether it is an irrational number. This is the kind of problem on which I am working, and I just wanted to complete my 2 courses by mentioning some problems which are related with my own research work. So I thank you very much, and I remind you that I would like to have your feedback, whether you prefer when I use the Blackboard or when I use the slides, and that will be helpful for me for when I give similar talks, courses online. Okay, thank you very much.
Okay, thank you. Let's give him a big applause. Okay. So maybe we should answer Professor Michel's Waldschmidt request. Which one do you prefer, fully from the whiteboard or? I think, yeah, for this afternoon, because I know in your time is in the morning.
Yes, yes, for me.
For us is in the afternoon. So
Okay.
I think, yeah, for today's session, yeah, is much clearer because there are many things that we can see, but for some details you are writing on the whiteboard. So
Yes.
I think, yeah, I think we prefer this one.
Oh, you prefer
Thank you
today?
very much. Yeah, prefer today.
Okay, good to know. Okay, thank you.
Yeah, because sometimes for some details we need handwriting also.
Yes.
Yeah. Okay, maybe any question before we end this session?
I'm not sure that I can see
the PDF. We have shared it in a lot. And actually you can find it in Professor Michel Waldschmidt's webpage.
Yes.
Yeah.
So I put it only this morning. I prepared it yesterday and this morning before giving my talk.
Okay, I think yeah, we can end this session.
Thank you very much.
Thank you very much. See you. Goodbye.
Bye.